Hi everyone, today exponential functions. Here we actually will see the use of transformations, and it will give us better understanding of that. So let's start. Exponential functions, we have already seen how to evaluate a to the power of n for any n that is rational. How do you evaluate a to the power of n where it's an irrational, where it's a real number? Let's see, we're using exponential functions for that. Okay, exponential function is y equals to the 2 to the power of x. So this is constructing a table of values, and then we plot the points, and this is what we actually get. We see as x becomes really large number and negative, we have an asymptote here, a horizontal asymptote, because the graph will never touch the x-axis, but it continues to become very close to it. X, as it becomes minus infinity, which is a negative big number, y becomes 0 from the positive side of it, from above the x-axis. This is y equals 0, is therefore a horizontal asymptote. And this is what we get. This is the curve that we get. Great. Here are some investigation. You can look in the book and even graph all those graphs and see what you get. All different a little bit, but from the investigation, we can discover the following things, okay? This is an exponential function because you see the unknown is here in the exponent, in the index. Now let's see what each part does. A controls how steep the graph increases or decreases, okay? Either that way or that way or that way. H controls horizontal translation. You see the x minus h, that is like an horizontal translation, which decides if the graph moves right or left. K here would be the vertical translation, whether the graph moves up or down, or the horizontal asymptote, does it move up or down? The equation of the horizontal asymptote is y equal k. So it's very easy to find because this is the one that is different from the function here by the plus or the minus sign. Now let's take a look here. This is what we just seen. This is the function of the exponential function looks like that. That's the regular one. As long as it's 2 to the power of x. Here, this is when a is between 0 and 1. This is a like half to the power of x. Then the function is like a reflection on the axis. Looks like that. 2 to the power of x and half to the power of x. This means because a is 2 to the power of x, but p is negative, that is minus 2 to the power of x, then we have a reflection of 2 to the power of x on the x-axis. And if this is a fraction, like half to the power of x, and this is negative, then that is a reflection of that one. Let's continue and see how it works. To sketch an exponential function, we need the horizontal asymptote, which we've seen, it's fairly easy to find. The y-intercept is when we substitute x 0 for x, and just substituting two other points, just finding two other points and plotting them. All exponential graphs have an horizontal asymptote, okay? Let's see this one. Sketch the graph of y equals 2 to the power of minus x minus 3. So this here would be the horizontal asymptote, minus 3. When we substitute 0 for x, we get the y-intercept. So y equals 2 to the power of 0 minus 3. Any number to the power of 0 is 1. 1 minus 3 is minus 2, so we get this one here, we get this one here, and there are two other numbers that were plotted and were found, this one, and then you just connect them. Let's continue. Consider the graph of 2 to the power of x alongside. Use the graph to estimate the value. Okay, if 2, the square root of 2 is actually 2 to the power of half. So that is actually x when x equals half. So I'm going here. This is x equals half. I'm going up to the graph. And that would be the y value of the square root of 2. 2 to the power of 0.8. So 0.8 is here. That would be for b. That would be y equals 1.8 or something like that. 2 to the power of 1/2, so and so. Use the graph to estimate the solution for 2 to the power of x equal 3. So now I'll go to the y equal 3, go here, and then I find what x is. So this is finding graphically. Great. Graphical methods can be used to solve exponential equations where we cannot equate indices as we've seen in the section before. Use the graph to explain why 2 to the power of x equals 0 has no solution. So we see 2 to the power of x equals 0, that means y equals 0, and we see it's a horizontal asymptote. Match, maybe that will make it more clearer. So when this is more than 1, then this would be C. You see, this is the regular graph, goes like that. So this would be C. 10 to the power of x is more steep, would be B. This one here, we need a fraction here, 1/3, that would be A. And those with the negative sign are reflections of the other. So this would be a reflection, E would be a reflection of the regular one, which is 2 to the power of x, or 10 to the power of x. So this would be that. It's a reflection of 5 to the power of x. And this would be a reflection where the base is a fraction between 0 and 1. So that is D. Negative, reflection, and half, because this is when it's a fraction. And a fraction is like a reflection of y equals 2 to the power of x on the y-axis. So that is flips like that when it's a fraction, and flips like that when it's negative. Draw freehand sketches of the following pairs of graph. Y equal 3 to the power. Okay, so let's do this one. 3 to the power of x will look something like that. 3 to the power of minus x will look something like that. It's a reflection on the y-axis. 3 to the power of x and 3 to the power of x plus 1. So this is 3 to the power of x, and this is 3 to the power of minus x. Why is that, by the way? Because this is equals actually, this is like 3 to the power of 1 to the power of x, which is 1/3 to the power of x. So this is why it's a reflection looking like that. 3 to the power of x plus 1. So there's a horizontal translation. It's going up by 1. 3 minus 3 to the power of x. So if this is 3 to the power of x, this would be a reflection on the y, on the x-axis. And 3 to the power of x minus 1, that's a translation in the horizontal. Because it's minus 1, you remember, it's counterintuitive, and then we move to the right a bit. So that will look like that. For 3 to the power of x minus 1. State the equation of the horizontal asymptote. So here it's 0, here it's y equals minus 1, y equals 0, y equals 3, not minus, y equals minus 4, and I think you got the idea. Consider the extent of time. Let's take a look here. This is consider the function g of x equal 3 times half to the power of x plus 4. Fine. So actually, we need really to substitute it. And then we get half to the power of 0 is 1. So that is 3 plus 4 is 7. So here, the y here is 7. This is y here is 4 3/4. And this would be half to the power of minus 2. We just change it into 2 to the power of 2, which is 4. So that would be 16. We can plot those points. Sketch the equation of the horizontal asymptote. That is a 4. So actually, we got some points, and we can work with those points. Let me just see again. Sketch the graph of the function. Okay, great. So this is a minus 2. Minus 2 is a 16. 0 is 7. And 2 is that. So it looks like that. As we said, because it's a fraction, it's looking like that. State the domain and range. That's what we want to focus on. So here the horizontal asymptote is y equals 4. So domain and range. Who remembers what does that mean? So the domain is all the possible x's. In this case, the domain is x, can be any real number, but the range is above 4 only. Is all the possible values of y. For each of the functions below, sketch the graph of the function, domain and range, the horizontal asymptote. Okay, so it continues. Let's see some more using that time, A and B, finding the values of A and B. So we have 2 points here that we can substitute, and then we have an equation that we can, 2 equations that we can find what is A and what is B. I hope that was clear, like 0 and minus 5. Then we get 2 equations with 2 unknowns, with 2 variables. And then y, and then we can just substitute 6 and find what y is. Use technology to solve the equation 3 to the power of x equals 7. So we go to the graph. We graph using the calculator. This would be when we graph 3 to the power of x. This would be the line of y equals 7. And then we find the intersection point. So use your calculator to find these. For the exponential function y equals y to the power of x, why do we choose to specify a is greater than 0? Why is that? Okay, because we know if it's to the power of 2, it's positive. If it's to the power of 3, it will be negative. Then it will be more complicated to solve. Practice a few. Using the book as well, you can find the final solution, and good luck.